morning, all of you. Today I am going to make an audio recording for visually impaired student of organic chemistry book. Name of the chapter is Alcohol. Introduction. Alcohol constitute a class of compounds which are regarded as hydroxy derivative of hydrocarbon. They are further classified as monodi and trihydric alcohol according as the number of hydroxyl group present in their molecule is 1, 2 or 3 respectively. Alcohol containing 4 or more hydroxyl group are known as polyhydric alcohol. Thus we have methyl alcohol monohydric, glycol dihydric, glycerol trihydric, sorbitol polyhydric. It may be pointed out that di, tri, and polyhydric alcohol always have the OH group attached to the different carbon atom. This is because a compound having more than one OH group linked to the same carbon atom is unstable and at once eliminates the element of water as shown below. Aromatic hydrocarbon compound fall into two categories. These are first aromatic alcohol. These are compound in which the hydroxyl group is present in the side chain. They may be regarded as alcohol in which OH group is attached to an aryl substituted alkyl radical. An important example of such a compound is benzyl alcohol. Second is phenols. These are compounds which contain hydroxyl group or group directly attached to an aromatic ring. For example, phenol is an important example. The properties of phenol are markedly different from the properties of alcohol and their chemistry is discussed separately in chapter 2. Monohydric alcohol. These are the alcohol having the general formula ROH, where R is maybe the simple or substituted alkyl group. Thus we have methyl alcohol, ethyl alcohol, benzyl alcohol. Saturated monohydric alcohol are also known as alcohols, as these are derivated from alkenes by the replacement of hydrogen atom by the hydroxyl group. Alkones can be represented by the general formula CnH2n plus 1 OH, where N is the number of carbon atom. Classification. Monohydric alcohol may be further classified as primary, secondary or tertiary alcohol as given below. First is primary alcohol. These are alcohol in which the hydroxide group is attached to the primary carbon atom, for example ethyl alcohol and propyl alcohol, benzyl alcohol. It is apparent that the carbon which carries the OH group has at least two hydrogen attached to it. In other words, primary alcohol have the characteristics group CH2OH present in them. Secondary alcohol. These alcohol contain the hydroxy group attached to the secondary carbon atom, for example isopropyl alcohol, secondary butyl alcohol. In these alcohol, the carbon carrying the OH group has only one hydrogen atom attached to it. As such, the characteristics group is in these alcohol is CHOH. Third is tertiary alcohol. These are alcohol in which the hydroxy group is attached to the tertiary carbon atom, for example tertiary butyl alcohol. It is clear that the carbon carrying the OH group has no hydrogen attached to it. This means that the characteristics group present in these alcohol is COH. Nomenclature of monohydric alcohol. Monohydric alcohol are named by three different systems. First is common system. According to this system, which is used only for the simple alcohol are named by adding the word alcohol to the name of alkyl group present in the molecule. For example, methyl alcohol, ethyl alcohol, and propyl alcohol, isopropyl alcohol, tertiary butyl alcohol, benzyl alcohol. Second is the carbonyl system. According to this system, methyl alcohol is called carbinol and other alcohol are named as alkyl derivative of carbonyl. For example, carbonyl, methyl carbonyl, dimethyl carbonyl, triphenyl carbonyl. However, this system is used only rarely. Third is the IUPAC system. In this system, alcohol are named in accordance with the general IUPAC rules. The main point involved in the nomenclature are summed below. First is the longest carbon containing chain. The carbon atom carrying the hydroxide group is selected as the corresponding to the parent hydrocarbon. The alcohol is named as derivative of the hydrocarbon by replacing the final E of the name of hydrocarbon by the suffix ol. Second is the parent chain of carbon atom is numbered from that end which gives the lowest possible number to the carbon carrying the hydroxyl group. Third is the name of the alcohol is then written as one word by writing the name of the side chain by or substituent along with their position in alphabetical order followed by the name of parent alcohol. For example, ethanol, butane 1 ol, 2-methyl propane 1 ol, 2-methyl propane 2 ol, 2-phenyl ethane 1 ol. The common and IUPAC name of few alcohol are given below. Structural isomerism. Monohydric alcohol exhibit three types of structural isomer. First is chain isomerism. This type of isomerism is due to the difference in the nature of carbon chain attached to the hydroxyl group. It is exhibited by alcohol having 4 or more carbon atoms. For example, butane 1 ol, 2-methylpropanol. Second is position isomerism. It is due to the difference in the position of hydroxyl group in the chain of the carbon atom. For example, butane 1-ol, butane 2-ol. In general, the total number of isomeric saturated monohydric alcohol is 2n minus 2, where n is the number of carbon atom. Thus, there are 8 isomeric alcohol having the molecular formula C5H11OH. Third is functional isomerism. Monohydric alcohol are exhibit functional isomerism with another class of oxygen derivative, namely ether. For example, ethanol, methoxymethane. Method of formation. Reduction of carbonyl compound alcohol can easily obtained by the reduction of aldehyde, ketone, carboxylic acid, ester, etc. by variety of reducing agent as discussed below. First is reduction of aldehyde and ketone. Aldehyde can be reduced to primary alcohol and ketone to secondary alcohol in number of ways as given below. First is catalytic hydrogenation. Aldehyde and ketone can easily be reduced to primary and secondary alcohol respectively by hydrogenation in the presence of catalysts such as nickel, palladium, or platinum, that is. Aldehyde in the presence of H2 nickel give rise to primary alcohol, and ketone in the presence of H2 nickel give rise to secondary alcohol. For example, propanoaldehyde in the presence of H2 nickel give rise to N-propyl alcohol. Catalytic hydrogenation of an aldehyde or ketone containing other easily reducible groups such as carbon-carbon double bond will furnish product in which both the functional group are reduced. For example, croton aldehyde plus H2 in the presence of nickel give rise to N-butyl alcohol. Therefore, this method cannot be used if it is desired to carry out the selective reduction of only carbonyl group, keeping the other group intact. Second is reduction with complex metal hydride. The reduction of aldehyde and ketone to prepare alcohol is usually carried out in the laboratory with complex metal hydrides such as lithium aluminium hydride and sodium boron hydride. Aldehyde or ketone in the presence of LiLH4 or NaBH4 in the presence of H3 positive ion give rise to primary or secondary alcohol. Sodium boron hydroxide hydride is easier to handle and can be used either in water or alcohol solution. The reduction product initially formed get hydrolyzed to form alcohol. For example, butanol in the presence of NaBH4, ethanol in the presence of H3 positive ion give rise to butane 1-ol. Lithium aluminium hydride react violently with water and alcohol. It can be used only in aprotic solvents such as dry ether or tetrahydrofuran. The product initially formed is then subjected to hydrolysis to get the alcohol. For example, but2-one in the presence of LiLH4 ether 3H3 positive ion give rise to but1-ol. Mechanism. Reduction of aldehyde and ketone by both LiLH4 and NaBH4 occur through the nucleophilic attack of hydride ion on the carbonyl group to form complex containing an OP or OAl bond. This species has still got 3 metal hydrogen bond and react further with 3 more molecule of carbonyl compound. The metal alkoxide intermediate thus formed is hydrolysis to get the alcohol as shown below. Reduction with NaBH4. It may be seen that 1 mole of NaBH4 or LiLH4 reduces 4 mole of aldehyde or ketone. Both LiLH4 and NaBH4 are selective in their reducing action. In the reduction of aldehyde and ketone containing isolated carbon-carbon double bonds, only the carbonyl group get reduced by these reagents. For example, hex 4 in 2-one in the presence of LiLH4 or NaBH4, H3 positive ion give rise to hex 4 in 2-ol. In case of compound which contain carbon-carbon double bond in conjugation with carbonyl group, sometimes the double bond may also get reduced along with the carbonyl group. The chances of reduction of both functional group are more with LiLH4 than with NaBH4. For example, cinnamaldehyde in the presence of LiLH4, H3 positive ion give rise to gamma phenyl propyl alcohol, and in the presence of NaBH4, H3 positive ion give rise to cinnamyl alcohol. Thus, NaBH4 is less vigorous and more selective than LiLH4. It may be recalled that a reagent which attacks only one functional group and not the other functional group is also present is known as regioselective reagent. A very effective regioselective reducing agent for carbonyl group developed recently is 9BB9 9-borabicyclo-111 no name. C is Mervin Ponto Veralli reduction. It is commonly used reduction for the reduction of ketone to secondary alcohol. The reaction is carried out by heating the carbonyl compound in isopropyl alcohol in the presence of aluminium isopropoxide, also known as Mervin Pondorf Barely reagent and distilling of acetone from the reaction mixture, the other functional group, if only any present in the carbonyl compound, remain unaffected. Ketone plus isopropyl alcohol in the presence of aluminium isopropoxide second give rise to secondary alcohol plus acetone distilled off. It is reversible reaction, but the equilibrium is pushed in the forward direction by distilling of acetone as soon as it is formed. Second is reduction of carboxylic acid. Primary alcohols can be obtained by the reduction of carboxylic acid by LiLH4. NaBH4 does not reduce carboxylic acid. In this reaction, the carboxylic part of carboxylic group is reduced to CH2 group. Carboxylic acid in the presence of LiLH4 ether and H3O positive ion give rise to primary alcohol. For example, butyric acid in the presence of LiLH4 ether H3O positive ion give rise to 1-butanol. Mechanism: the reaction takes place through the formation of intermediate alkoxide which yields the alcohol and hydrolysis. This method is generally employed for the preparation of alcohol from acid which are readily available for natural sources. Carboxylic acid can be also reduced rapidly to primary alcohol by the action of diborane. Third is reduction of ester. Reduction of ester constitutes of convenient method of preparation of alcohol. The reduction is generally carried out by the following method. Solvent-black reduction. This method involves the reduction of ester to alcohol by treatment with sodium in the alcohol. The reaction leads to the formation of a mixture of two alcohol, one which is formed from the alkoxy group and the second which is formed from the acyl group. Ester in the presence of sodium C2H5OH give rise to 2 moles of alcohol. For example, ethyl propanoid in the presence of sodium C2H5OH give rise to 1 propanol plus ethanol. Mechanism: the reaction is believed to take place in a number of steps and involves the transfer of one electron at the time from sodium metal as summed up ahead. Second is reduction with LiLH4. Ester can also be reduced with LiLH4 to yield a mixture of two alcohol as in case of Baldwin-Blank reduction. For example, ethyl purate in the presence of LiLH4 ether H3O positive ion give rise to 1-butanol plus ethanol. Mechanism: the reaction takes place by the addition of hydride ion to the carbonyl part of ester group. This is followed by elimination of alkoxide ion to yield an aldehyde intermediate which is not isolated. Further reaction of LiLH4 with aldehyde gives primary alcohol. C is catalytic hydrogenation. On an industrial scale, alcohol are obtained from ester by catalytic hydrogenation in the presence of copper chromite catalysis. For example, ethyl propanoid in the presence of copper chromite give rise to 1-propanol plus ethanol. Physical properties of alcohol: due to the presence of OH group in their molecule, alcohol are polar compound. Oxygen is more electronegative than either carbon or hydrogen, so that electrons of the CO as well as OH bonds are displaced towards the oxygen atom. Therefore, the oxygen atom carry partial negative charge while both carbon and hydrogen attached to oxygen carry partial positive charge. Moreover, like water, alcohol molecule also have a band structure so that we may represent alcohol molecule as. Because of their band structure and polar nature of carbon-oxygen and oxygen-hydrogen bond, alcohol possess considerable dipole moment. The above structural feature of alcohol have a strong influence on physical and chemical property of alcohol as discussed below. First is physical property. The lower alcohol are colorless liquid having a distinct alcoholic smells and a burning taste. The higher member are colorless, tasteless, waxy solid. Second is associated state hydrogen bonding. Since alcohol contain hydrogen attached to strongly electronegative atom, extensive intermolecular hydrogen bonding exists between alcohol molecule. As a result, alcohol exists in the form of associated molecule and not simple monomeric molecule. Third is boiling point. The boiling point of alcohol are much higher than those of hydrocarbon or ether of comparable molecular weight, as is evident from the following example: ethyl alcohol, dimethyl alcohol, and propane. Boiling point is 351.5 and that of dimethyl ether is 249 and propane is 231. The higher boiling point of alcohol can be explained in terms of extensive intermolecular hydrogen bonding in alcohol. Large amount of energy is required to break these hydrogen bonding which hold the alcohol molecule together in the associated state. Therefore, alcohol boils at much higher temperature than alkanes, ether, etc., which do not form intermolecular hydrogen bonds amongst themselves. The boiling point of isomeric alcohol are in the order primary, secondary, tertiary. This is because out of isomeric alcohol, primary alcohol are most polar and form hydrogen bonds to the maximum extent as compared to secondary and tertiary alcohol. With the increase in molecular weight, the boiling point increases regularly. Solubility. The lower alcohol are highly soluble in water, but the solubility decreases with increase in molecular weight. The high solubility of lower alcohol is due to the formation of hydrogen bond between alcohol and water molecule. The rapid fall in solubility of higher alcohol is due to the fact that with the increase in molecular size, the non-polar hydrocarbon character of molecule become more dominating in comparison with the polar OH group. This leads to decrease in extent of hydrogen bond formation with water, and therefore the solubility in water decreases. For isomeric alcohol, the solubility increases with increase in branching. This is because of the reason that as branching increases, surface area decreases. The high alcohol, it may be noted, are more soluble in organic solvent density. Generally speaking, the density of alcohol is lesser than that of water, although it increases with the increase in molecular weight. Chemical properties. The hydroxyl group present in alcohol is a very reactive group, and the characteristics reaction of alcohol are the reaction of OH group. In general, the reaction of alcohol may be divided into following three categories. First is reaction involving the cleavage of OH bond. Second is reaction involving the cleavage of COH bond. Third is reaction involving both alkyl and hydroxyl group of the alcohol molecule. Reaction involving the cleavage of OH bond. The general order of reactivity of alcohol in this type of reaction is primary alcohol, secondary alcohol, tertiary alcohol. Explanation. In the cleavage of OH bond, oxygen, which is more electronegative than hydrogen, take away both the electron of the shared electron pair. Therefore, the relative reactivity of alcohol in this reaction can be explained in terms of electron releasing inductive effect of alkyl group. As we move from primary to secondary to tertiary alcohol, the number of alkyl group attached to the carbon carrying the OH group increase from 1 to 3. Due to this, the electron density around oxygen goes on increasing on moving from primary to secondary to tertiary alcohol. Primary alcohol, secondary alcohol, tertiary alcohol. The result in this that the electron of the OH bond cannot be sufficiently drawn towards oxygen, and the ease of cleavage of OH bond decreases. Thus, the order of reactivity in the reaction involving the cleavage of OH bond is primary, secondary, and tertiary. It can be easily understood that methyl alcohol, which has only 3 hydrogen attached to the carbon carrying OH group, would be most reactive of all alcohol. First is reaction with metal. Acidic nature. Alcohol react with active metal like sodium, potassium, magnesium, alcohol, aluminium to liberate hydrogen and form metal alcoholates and alkoxide. For example, ethyl alcohol gives rise to sodium ethoxide. This reaction suggests that alcohol are acidic in nature. This is quite understandable since the OH group contain highly electronegative oxygen attached to hydrogen. Naturally, the OH bond is polarized in character and allow the separation of hydrogen as H positive ion. However, alcohol are very weak acid, even weaker than water. This is because of alkyl group present in alcohol have an electron releasing inductive effect. This causes an increased electron density around oxygen. The result is that electrons of the OH bond are not sufficiently drawn towards oxygen, and the release of proton is rendered difficult. In other words, the plus I effect of alkyl group makes the alcohol weaker acid than water. Comparison of acid strength of 1 degree, 2 degree, and 3 degree alcohol. Since the plus I effect would be maximum in tertiary alcohol, which have 3 alkyl group attached to the carbon bearing the OH group, and least in primary alcohol having only one alkyl group attached to the carbon of OH bond. The order of acidity of alcohol is primary, secondary, and tertiary. It is evident that methyl alcohol would be stronger even than ethyl alcohol and other primary alcohol since it has no alkyl group attached to the carbon carrying OH group. Second is reaction with Grignard reagent. Alcohol reacts with Grignard reagent to produce hydrocarbon as shown below. Alcohol plus Grignard reagent give rise to hydrocarbon. For example, methyl alcohol plus ethyl magnesium iodide give rise to ethene. It may be noted that alkene form correspond to alkyl group of Grignard reagent. Third is reaction with organic acid. Alcohol react with organic acid to form ester. This is a slow reversible reaction termed as esterification. It is generally carried out in the presence of concentrated sulfuric acid or hydrogen chloride gas. Acid plus alcohol give rise to ester plus H2O. The reaction is reversible in nature, but the equilibrium can be pushed in forward direction by removing the water formed continuously. This is done with the help of an apparatus called Dean and Stark separator. If esterification is carried out in the presence of HCl, it is known as Fischer-Spire esterification. For example, acetic acid plus ethyl alcohol in the presence of HCl gas give rise to ethyl acetate plus water. Mechanism. The mechanism of esterification involves the initial protonation of carbonyl oxygen of carboxylic acid by the proton released by the mineral acid. As a result, carbonyl carbon become more positively charged and readily undergoes nucleophilic attack by oxygen of the alcohol. The resulting intermediate is ultimately converted into the ester as depicted below. Isotopic trigger studies have confirmed that esterification involves the cleavage of OH bond of alcohol and COH bond of acid, as suggested by the APO mechanism. For instance, let us consider the esterification reaction of acetic acid with ethyl alcohol having an isotope of oxygen of atomic weight 18 in the hydroxyl group. At the conclusion of the esterification reaction, the isotopic oxygen would be found to be present in ester and not in water, as shown below. Relative reactivity of alcohol and acid. The relative reactivity of alcohol and acid in this reaction are strongly influenced by steric hindrance caused by the presence of large group in them. The greater the size of group near the OH group of alcohol or carboxylic group of acid, the slower the rate of esterification. For example, the decreasing rate of esterification of some alcohol and acid are alcohol CH3OH greater than CH3CH2OH greater than CH3 twice CHOH greater than CH3 thrice COH. Acids HC double bond OOH greater than CH3 C double bond OOH greater than CH3 twice CH C double bond OOH greater than CH3 thrice C double bond OOH. Fourth is reaction with acid halide or acid anhydride. When alcohol are heated with an acid halide or acid anhydride, the hydrogen of OH group is replaced by acyl group and once again an ester is formed. The reaction known as acylation takes place more rapidly than esterification with carboxylic acid themselves. Thus, we have acetyl chloride plus CH2 C2H5OH give rise to ethyl acetate plus HCl, and in the presence of acetic anhydride, it gives ethyl acetate plus acetic acid. It may be noted that in case of polyhydric alcohol, hydrogen of each OH group is replaced by acyl group to form polyester. For example, 1 mole of glycerol reacts with 3 moles of CH3COCl to form a triester. Mechanism. The reaction mechanism may be depicted as follows. Reaction involving the cleavage of carbon hydroxyl bond. In this reaction, the bond between carbon of the alkyl group and oxygen of hydroxyl group get ruptured. The order of reactivities of alcohol in this type of reaction is tertiary alcohol, secondary alcohol, primary alcohol. Explanation. The above order of reactivities can be explained in terms of plus effect of alkyl group. As we move from primary to secondary to tertiary alcohol, the number of alkyl group attached to carbon carrying the OH group increases. Due to this, the electron of COH bond are pushed more and more towards oxygen. As a result of COH bond become more and more polar and therefore more reactive. In other words, tertiary alcohol would be most reactive in such reactions, and the reactivity will be lesser and still lesser in case of secondary and primary alcohol. It is also evident that methyl alcohol would be least reactive of all alcohol. First is reaction with hydrogen halide. Alcohol react with hydrogen halide to form alkyl halide, and water alcohol plus HX give rise to alkyl halide plus H2O. For example, ethyl alcohol in the presence of HCl gas and anhydrous ZnCl2 give rise to ethyl chloride plus H2O. Hydrogen bromide and hydrogen iodide react in the same way as shown above in case of hydrogen chloride, but without in the presence of dehydrating agent anhydrous ZnCl2. If an alcohol is heated with hydrogen iodide in the presence of red phosphorus, it gets reduced to hydrocarbon. For example, methyl alcohol plus 2HI in the presence of phosphorus give rise to methane plus H2O plus I2. The order of reactivity of halogen acid is Hi, HBr, HCl, while the order of reactivity of alcohol is tertiary, secondary, and primary. Due to its lower reactivity, the reaction of hydrogen chloride with primary and secondary alcohol requires the use of catalysts such as anhydrous zinc chloride. Due to the difference in the reactivity of 1 degree, 2 degree, and 3 degree alcohol with halogen acid, the reaction of HCl and anhydrous ZnCl2, known as Lucas reagent, is used for distinguishing between different classes of alcohol. Tertiary alcohol react with Lucas reagent immediately to produce a cloudness due to the formation of alkyl chloride. Secondary alcohol react with Lucas reagent less rapidly to produce a cloudness after 2-3 minutes. Primary alcohol react with Lucas reagent only on heating and no cloudness is produced in the cold. Mechanism. The mechanism of the reaction is believed to follow except in case of methanol and most of the primary alcohol. This is obviously in SN1 mechanism involving a protonated alcohol as the substrate and the halide ion as the nucleophile. This mechanism is supported by the fact that the observed order of relative reactivity of alcohol is the same as the order of stabilities of the carbocation. The formation of rearranged product in many cases further supports the intermediate formation of carbocation. For example, alternate mechanism. It has been observed that primary alcohol other than neophenyl alcohol do not form rearrangement product. To account for this, an alternate SN2 mechanism which does not involve the formation of carbocation intermediate has been proposed for methanol and most of the primary alcohol. Thus we have second is reaction with phosphorus halide. Alcohol react with phosphorus halide PCl5, PCl3, PBr3 or Pi3 to yield corresponding alkyl halide. Alcohol plus PCl5 give rise to alkyl chloride plus PoCl3 plus HCl. For example, benzyl alcohol plus PCl5 give rise to benzyl chloride plus PoCl3 plus HCl. Alcohol plus PX3 give rise to alkyl halide. For example, ethyl alcohol in the presence of Pi3 give rise to ethyl iodide. Mechanism. The mechanism of the reaction between alcohol and PX3 may be illustrated by considering the reaction between an alcohol and PCl3 as given below. In the first step, nucleophilic attack of alcohol on PCl3 take place to form a protonated alkyl dichlorophosphate. In the second step, chloride ion act as nucleophile and displace HOPCl2 from the phosphate initially formed. HOPCl to react with more alcohol by the repetition of step first and second to form RCl, NOH2 PCl. Further reaction between HO twice PCl and alcohol by step first and second give rise to another molecule of RCl and OH3P or H3PO3. Thus, the reaction ultimately lead to conversion of 3 moles of alcohol into alkyl chloride by 1 mole of PCl3. The following mechanism has been proposed for the reaction between alcohol and PCl5. Third is reaction with thionyl chloride. Alcohol react with thionyl chloride preferably in the presence of base such as tertiary amine to form alkyl chloride. Alcohol plus thionyl chloride give alkyl chloride. For example, ethyl alcohol plus SOCl to give rise to ethyl chloride plus SO2 plus HCl. The base promotes the reaction by reacting with HCl. This is tertiary amine plus HCl give rise to R3NH plus Cl negative. Mechanism. The reaction is believed to take place as follows. Reaction involving both alkyl and hydroxy group. First is acidic dehydration. When alcohols are heated with sulfuric acid, phosphoric acid or boric acid, or when their vapors are passed over heated aluminium oxides which act as a Lewis acid, alcohol get dehydrated to form alkene. For example, ethyl alcohol in the presence of H2SO4 433 to 443 Kelvin gives ethylene plus H2, and butyl alcohol in the presence of H2SO4 loses molecule give rise to 2-butene, main product formed through rearrangement and plus 1-butene. The reaction between alcohol and sulfuric acid is very sensitive to condition of reaction for furnishing different product under different condition. For example, when ethyl alcohol is treated with sulfuric acid, ethyl hydrogen sulfate is obtained as at 383 Kelvin. Ethyl hydrogen sulfate so produced when subjected to specific condition gives the following three different products. First, on distillation under reduced pressure, ethyl hydrogen sulfate formed diethyl sulfate. When heated to 413 in Kelvin in the presence of excess of alcohol, ethyl hydrogen sulfate react further to give ether. See, on the other hand, if heated to 433 to 443 Kelvin in the presence of excess of sulfuric acid, ethyl hydrogen sulfate changes to ethylene. Mechanism of dehydration. The mechanism of dehydration of alcohol involved in the formation of carbocation as an intermediate. The reaction is believed to take place in the three steps. In the first step, alcohol combined with hydrogen ion form from the acid to form protonated alcohol or oxonium ion. The second step involves the dissociation of oxonium ion and formation of carbocation. Finally, the carbocation loses a hydrogen ion to a fresh molecule of alcohol to yield the alkene. The various steps are illustrated ahead with the help of ethyl alcohol. All the three steps shown above involve reversible equilibria. However, the resulting alkane is much more volatile than the starting alcohol and is easily driven out from the reaction mixture. The shift in equilibrium in step 3 towards the right consecutively, the entire reaction is pushed to completion. It may be noted that the dissociation of oxonium ion requires the supply of energy. This is made available through the solvation of carbocation, considerable energy being released by the setting up of ion dipole bond between the carbocation and the solvent molecule. Relative ease of dehydration of alcohol. It has been observed that ease of dehydration of different classes of alcohol follow the order tertiary, secondary, and primary. To account for this observed order, let us consider the rate of determining step in the dehydration of alcohol, that is, the dissociation of protonated alcohol to form carbocation. This step, including transition state involved in it, may be depicted as the positive charge may be noted is originally on the oxygen, but in the product it is on carbon. In the transition state in which the carbon oxygen bond is beginning to break, the positive charge is partially on oxygen and partially on carbon. This means that the transition state has acquired some carbocation character. As such, the same factor it means dispersal of positive charge, which increase the stability of carbocation, would increase the stability of transition state, leading to that ion and lower its E activation. This means that transition state leading to the formation of tertiary cation, which is more stable ion, would be more stable and therefore have least activation energy. In other words, such a transition state and the carbocation generated by it would be formed more rapidly. Consecutively, the dehydration of tertiary alcohol would take place more readily. The dehydration of secondary alcohol, which involved the formation of less stable secondary cation, would naturally take place less easily. Similarly, involve the dehydration of primary alcohol involving the least stable primary cation would be the most difficult to take place. Thus, the relative ease of dehydration of alcohol follow the same order as of the ease of formation of carbocation. Orientation of dehydration. Many alcohol give rise to mixture of isomeric alkene. On dehydration, the ratio of alkene formed in the particular reaction depend upon the reaction condition. However, in general, it may be stated that dehydration of alcohol favor the formation of more stable alkene. For example, secondary butyl alcohol give rise to two products. One is 1-butene that is less stable and second is 2-butene that is more stable. Both the isomeric butene are obtained by the exclusion of H positive ion from the same carbocation formed as an intermediate as shown below. This implies that the stability of carbocation cannot have any effect on the ratio of product obtained. It may noted, however, the chief product is more stable than the other since it is more highly substituted. A similar situation exists in the dehydration of 2-methyl 2-butanol with 15% H2SO4 at reflux temperature. Here again, the more highly substituted product and therefore more stable product is formed in predominating quantities. To sum up, it may be stated that dehydration of alcohol favored the formation of more stable alkene. Rearrangement of carbocation and formation of unexpected product during dehydration. It has been found that during the dehydration of alcohol, some of the alkene formed are not what one would normally expect. The position of double bond formed or sometime even the carbon skeleton may be quite unexpected. For example, the dehydration of N-butyl alcohol give a mixture of 2-butene and 1-butene, whereas normally only 1-butene should be formed. The formation of unexpected product as shown above can be explained in terms of the rearrangement of intermediate carbocation. It has been observed that carbocation tends to rearrange to form more stable ion. This rearrangement usually involves the migration of hydride ion. It means hydrogen along with the pair of bonding electron from the adjacent carbon atom to the positively charged carbon of carbocation shift. Such a migration is known as hydride shift. Alternatively, the rearrangement may occur through the migration of an alkyl group with its pair of bonding electron from an adjacent carbon to the carbon having the positive charge. This type of migration is known as alkyl shift. Since such migration generally involve only two adjacent carbon, therefore they are termed as 1,2 shift. Example of hydride shift in the dehydration of N-butyl alcohol, the intermediate carbocation initially formed is N-butyl carbocation, which is a primary ion. This undergoes 1,2-hydride shift to form the more stable secondary butyl ion. This ion in turn loses as H positive ion to form the more stable 2-butene as preferred product. Example of alkyl shift in the dehydration of 3,3-dimethyl 2-butanol. The carbocation initially formed is a secondary carbocation. It means 3,3-dimethyl 2-butyl ion. This undergo the migration of methyl group with a bonding pair of electrons from an adjacent to the positive carbon to form the more stable tertiary carbocation, namely 2,3 dimethyl 2-butyl ion. The ion thus formed loses a hydrogen ion to form 2,3-dimethyl 2-butene as the main product, which is more stable than the expected product 3,3-dimethyl 1,1-butene. Partial dehydration of alcohol to form ether and the mechanism of reaction are discussed later in section 6.3, reaction number 3. Second is oxidation. Oxidation of alcohol can be carried out with a variety of reagents such as aqueous, acidified or alkaline potassium permanganate, acidified sodium or potassium dichromate, dilute nitric acid or CrO3 in pyridine. The ease of oxidation and the nature of product obtained depend upon the type of alcohol employed. First is primary alcohol are easily oxidized to aldehyde and then to acid containing the same number of carbon atom as the original alcohol. For example, ethyl alcohol give rise to acetyl aldehyde give rise to acetic acid on oxidation. It is possible to arrest the reaction at the aldehyde stage by using a suitable oxidizing agent such as acidified K2Cr2O7 and distilling away the aldehyde as soon as it forms. Second is secondary alcohol on oxidation first gives ketone with the same number of carbon atom. Ketones are further oxidized only on drastic treatment to give acid containing lesser number of carbon atom. For example, isopropyl alcohol on oxidation give rise to acetone, which further on oxidation give rise to acetic acid. Third is tertiary alcohol fails to undergo oxidation in neutral or alkaline solution. However, with acid oxidizing agent, they are oxidized to give ketones and acid containing lesser number of carbon atom than the original alcohol. For example, tertiary butyl alcohol on oxidation give acetone, which further on oxidation give acetic acid. Third is action of hot reduced copper. Different classes of alcohol furnish different product when their vapor are passed over reduced copper at high temperature 475 to 575 Kelvin. First is primary alcohol are dehydrogenated to form aldehyde. For example, ethyl alcohol in the presence of copper 575 Kelvin give rise to acetaldehyde. Secondary alcohol are also dehydrogenated to give ketone. For example, isopropyl alcohol in the presence of copper 575 Kelvin gives acetone. Third is tertiary alcohol are dehydrated to give alkene. For example, tertiary butyl alcohol in the presence of copper 575 Kelvin temperature give rise to isobutylene. Butylene. Distinction between primary, secondary, and tertiary alcohol. Lucas test. The most convenient and commonly used method for the distinguishing between different classes of alcohol is Lucas test. It consists in the treatment the alcohol with Lucas reagent, which is an equimolar mixture of concentrated hydrochloric acid and anhydrous zinc chloride. Appearance of cloudiness in the reaction mixture indicate the conversion of alcohol into alkyl chloride. It has been observed that tertiary alcohol react immediately and therefore cloudiness appear immediately. Secondary alcohol react within about 5 minutes when the cloudiness appears. A primary alcohol does not react appreciably at room temperature and therefore no cloudiness appears. An older method for distinguishing between primary, secondary, and tertiary alcohol, known as Victor Meyer method, is seldom used these days. Hydric alcohol. Dihydric alcohol are compound containing two hydroxyl group attached to different carbon atom in their molecule. They are known as diols in IUPAC system and glycols in common system. For example, ethane diol, ethylene glycol, or propylene glycol. Nomenclature. First is common name. The two hydroxy group in glycol are usually attached either to adjacent carbon atom or carbon atom situated at the extreme ends of carbon chain called polymethylene glycol. In the common system, vicinal glycols are named after the common name of corresponding alkane with while polymethylene glycol are named according to the number of methylene groups present in the molecule as given below. Ethylene glycol, propylene 1,2, glycol, trimethylene glycol. Glycols which are neither vicinal nor polymethylene are also named after parent alkene by specifying the position of hydroxyl group by suitable number. For example, butylene 1,3 glycol. Sometimes the position 1,2, 1,3 and 1,4 etc. are indicated by alpha 1,2, beta 1,3 and gamma 1,4 etc. For example, alpha propylene glycol, beta butylene glycol. Second is IUPAC name. In the IUPAC system, all dihydric alcohol are named as diols of parent alkane, the position of OH group being indicated by suitable numbers as given below. First is longest state carbon chain atom, which must include the two carbon carrying the OH group is selected and the name of corresponding hydrocarbon is written. Second, the chain is numbered from the end, which gives the lowest possible number to the carbon carrying the first OH group. Third is the suffix diol is added to the name of parent hydrocarbon along with the position of OH group. Fourth is the name of the side chain and the other substituent, if any, are prefixed before the name of the diols along with their position in alphabetical order. For example, ethane 1,2 diols, propane 1,2 diols, propane 1,3 diols, 2,3 dimethyl butane, 2,3 diols, 1,2 diphenyl ethane, 1,2 diols. Method of formation. The main methods used for the formation of glycols are given below. First is hydroxylation of alkanes. Glycol can be prepared conventionally by the hydroxylation of alkane by treatment with potassium permanganate solution or osium tetroxide. For example, ethylene in the presence of KMnO4/H2O give rise to ethylene glycol. The reaction is known as cis hydroxylation as it proceeds in the stereospecific manner leading to the formation of cis diols. For example, cyclopentane in the presence of KMnO4/H2O give rise to cis cyclopentane 1,2 diols. Second is hydrolysis of epoxide. Glycols can also be prepared by acidic catalyst hydrolysis of epoxide, which involves the cleavage of epoxide ring. For example, ethylene oxide in the presence of H2H positive ion give rise to ethylene glycol. It may be noted that hydrolysis of epoxide is also stereospecific and lead to the formation of trans-diol. For example, cyclopentane oxide in the presence of H2H positive ion give rise to trans-cyclopentane 1,2-diol. Epoxide themselves are usually prepared by treating alkene with peroxide acid. For example, ethene plus peroxoformic acid give rise to ethylene oxide plus formic acid. Third is hydrolysis of dihaloalkene. Diols can be easily prepared by the hydrolysis of dihaloalkene. For example, fourth is bimolecular reductions of carbonyl compound when treated with magnesium in an inert solvent such as benzene and ether under alkaline condition. Aldehyde and ketone undergo bimolecular reduction to form vicinal glycols. The mechanism of this reaction is discussed later under aldehyde and ketone. Fifth is reduction of dicarbonyl compound. Diols can be prepared by the reduction of dicarbonyl compound just as monohydric alcohol can be prepared by reducing aldehyde and ketone. For example, butane 1,4 diol in the presence of H2 nickel gives butane 1,4 diol. Reaction of diketone with Grignard reagent. This method can be used for the preparation of higher vicinal glycols. For example, butane 1,2 dione give rise to 1,2 glycol. Physical property. First is physical property. Physical state. Glycols are generally colorless. Viscous liquids have a sweet taste. Second is high melting and boiling point. Glycol undergo intermediate hydrogen bonding to the greater extent than monohydric alcohol. This is because they contain two sites for hydrogen bonding per molecule. As a result of extensive hydrogen bonding, glycol have much higher melting and boiling point as compared to monohydric alcohol. For example, the boiling point of ethylene glycol is 470 Kelvin as compared to ethyl alcohol. Third is solubility. Glycol have greater solubility in water than monohydric alcohol. This is again due to the more extensive formation of hydrogen bond between glycol and water than between monohydric alcohol and water. Chemical reactions. Like monohydric alcohol, glycol exhibits the usual reaction of hydroxyl groups such as reaction with metal like sodium reactions with halogen acid, esterification, etc. At the same time, glycol undergo certain reactions that are typical only of alcohol having two or more alcoholic group. We will now illustrate the important reaction of glycol by taking vicinal glycols as typical example. First is reaction with metal acidic nature. Like monohydric alcohol, glycol react with metal like sodium to form mono and disodium derivative and liberated hydrogen. For example, ethylene glycol in the presence of sodium 333 Kelvin gives monosodium glycolate, and in the presence of sodium 433 Kelvin give rise to disodium glycolate. It may be noted that the two H group react one by one at the same time. The second OH group reacts slowly as compared with the first. This is because in the diol molecule, the electron attracting inductive effect of one of the hydroxy group made the other hydroxy group more acidic in nature and it reacts with metal quite rapidly. But in the product formed in the first stage, the CH2O negative part exert an electron releasing effect which decreases the acidic character of second OH group. Second is the reaction with hydrogen halide. It reacts with HCl and HBr to form two different products as shown below. Ethyl glycol plus HCl give rise to ethylene chlorohydrin, and in the presence of HCl 473 Kelvin give rise to ethylene dichloride. It may be noted that the first stage of reaction takes place more rapidly than the second. This can be understood in the term of mechanism of the reaction. The reaction involves the initial protonation of OH group to form oxonium ion, which then undergoes nucleophilic attack by the halide ion chlorine or bromine to form the halo derivative. After the substitution of one OH group by chlorine or bromine, the electron density around the oxygen of the second OH group decreases because the strong electron attracting inductive effect of chlorine. As a result, protonation of second OH group does not take place easily. With HI, diiodide form decompose to give the alkene, for example. Third is reaction with PCl5 or thionyl chloride. Glycol react with phosphorus pentachloride or thionyl chloride to form dichloride. Reaction with phosphorus trihalide. When treated with PCl3 or PBr3, glycols form dichloride or dibromide. However, with Pi3, diiodide first form being unstable decomposed to give alkene and iodine, for example.
Fifth is reaction with nitric acid when heated with concentrated HNO3 in the presence of concentrated H2SO4 glycol form dinitrate. For example, dehydration. Dehydration of glycol under different conditions gives different product. This is illustrated below by considering the example of ethylene glycol. First, when heated to nearly 775 Kelvin, ethylene glycol forms ethylene oxide. Second, when treated with anhydrous zinc chloride under pressure in a sealed tube, ethylene glycol get dehydrated to form acetaldehyde formed through arrangement of vinyl alcohol. Third is when distilled with concentrated H2SO4, glycols form dioxane as shown below, and fourth on heating with concentrated H3PO4 ethylene glycol form diethylene glycol. Seventh, reaction with aldehyde and ketone. Glycol undergo condensation with aldehyde and ketone in the presence of p-toluene sulfonic acid, commonly called PTS, to form cyclic acetals. For example, the compound formed by the reaction of ketones with glycol were earlier termed as cyclic ketyls, but now the term cyclic acetal is used both in case of aldehyde and ketone. Eighth is reaction with organic acid. Glycols react with organic acid to form mono or diester depending upon the relative amount of glycol and the acid. Ninth is oxidation. Glycol give different product on oxidation under different condition. In general, the oxidation may be depicted as follow by considering the example of ethylene glycol. Glycol on oxidation gives glycoaldehyde, which further on oxidation with glycolic acid. Glycol on further oxidation gives glyoxyl, which further oxidation gives glyoxylic acid, which further oxidation gives oxalic acid. When oxide with nitric acid, ethylene glycol ultimately gives oxalic acid even though the intermediate product can be isolated. Oxidation cleavage of 1,2-glycol. When treated with periodic acid or lead tetraacetate compound containing 2 OH group attached only to adjacent carbon atom undergo oxidative cleavage. The reaction breaks carbon-carbon bond and yield carbonyl compound, aldehyde, ketone, etc. on oxidation product, thus that is. It may be noted that for every carbon-carbon bond broken, an additional carbon-oxygen bond is formed at each carbon. It may be noted that in these reactions, periodic acid is found to work well in aqueous solution, while lead tetraacetate gives good result in organic solvent. The oxidative cleavage of 1,2-glycols with periodic acid is also known as Malaprade reaction. Utility of the reaction. The reaction usually takes place in quantitative yield and is very useful in structural determination, particularly in the study of carbohydrate, which are polyhydroxyaldehyde or ketone. It gives valuable information by determining the quantities of oxidizing agent used and the nature and amount of product formed as illustrated below. First is structure determination. Let us consider the oxidative cleavage of three isomeric butane-diols, 1,2-butane-diols, 2,3-butane-diols, and 1,3-butane-diols, which with periodic acid. First is 1,2-butanediol react with 1 mole of HiO4 to give a mixture of formaldehyde and propanaldehyde. Second is 2,3-butanediol also react with 1 mole of HiO4 to give only acetaldehyde. Third is 1,3-butanediol does not react with HiO4 because it does not have the OH group attached to the adjacent carbon atom. Thus, the study of reaction with HiO4 can lead to the structure elucidation of the given diols. Second is determination of number of OH group on adjacent carbon. In case of polyhydric alcohol, the number of moles of oxidizing agent used in the reaction also indicate the number of OH group present on adjacent carbon. For example, 1 mole of glycol react with 2 mole of HiO4. This establishes the presence of 3 OH group on the adjacent carbon as shown below. Third is to determine whether the OH group are present in vicinal position or not. Qualitatively, the occurrence of reaction between polyhydric alcohol and HiO4 is established by the formation of white PPT of AgIO3 on adding AgNO3 solution to the reaction mixture. If the PPT is formed, it means that the given polyhydric alcohol react with HiO4, therefore it must have OH group attached to the adjacent carbon. On the other hand, if no PPT is formed, it means that the given alcohol does not react with HiO4 and the OH group are not attached to the adjacent carbon. Mechanism. First is oxidation with periodic acid. Oxidative cleavage with periodic acid is believed to take place through a cyclic intermediate formed by the attack of periodate ion on glycol as shown below. Second is oxidation with lead tetraacetate. This reaction is also believed to occur through a cyclic intermediate which undergoes on an oxidation reduction process leading to the cleavage of carbon-carbon bond. 11th, pinacol-pinacolone rearrangement. It is a typical reaction of higher glycol involving formation of rearranged product. It was first observed in case of pinacol 2,3-dimethyl 2,3-butadienol and hence the name pinacol rearrangement. It was found that on treatment with sulfuric acid, pinacol undergo dehydration with molecular rearrangement to form methyl tertiary butyl ketone, also known as pinacolone, that is 2-methyl 2,3-dimethyl 2,3-butadiol or pinacol. On reaction with H positive ion gives pinacolone. Many other vicinal glycol are now known to undergo similar acid catalyst reaction. All these reactions are therefore collectively known as pinacol-pinacolone rearrangement. Mechanism: the pinacol rearrangement takes place through stepwise mechanism as depicted below. Step first involve protonation of pinacol. Second step, the protonated species loses a water molecule to form a carbocation. In third step, the carbocation undergo rearrangement involving a 1-2 shift of the electron deficient carbon to generate a new, more stable ion. Thus, ion in turn eliminate a hydrogen ion to yield the final product. In some cases, the step involving removal of water and shift of alkyl group may take place simultaneously. Important observation. First is relative stability of carbocation. In case of glycol having different group attached to the 2-hydroxy group, the OH group which get eliminated is one which would produce a more stable carbocation. For example, second is migratory aptitude of groups. In case of glycol having different group attached to 2-hydroxy group, it is quite easy to predict the migratory aptitude of the group. In general, phenyl group migrates in preference to alkyl group and hydrogen migrates in preference to both these groups. The above reaction clearly shows that in order to predict the final product of pinacolone rearrangement, the relative stability of the carbocation intermediate as well as relative and migratory aptitude have to be taken into consideration. Stereochemistry. It may be emphasized that the migrating group, methyl group in the given example under mechanism is not completely detached from the carbon. It is leaving till it has attached itself to the electron deficient carbon as shown below. This would naturally mean that the migrating group in pinacolone rearrangement was retain its configuration. The new bond formed will have the same relative position as the held previously by the old bond. If the migrating group were to get completely detached before attaching itself to the electron deficient carbon, it would lead to racemization in case of chiral structure, but actually no racemization takes place. Thank you.